Determine the derivative for each of the following. For part A, we have the function f of x equals sine of 3x. And we have a formula that allows us to differentiate sine functions of the form sine of ax, and we know that that simply differentiates to a times cos of ax. So for this question, we would have f dashed of x, the derivative, is going to equal, the a value is 3, it's the coefficient of x, so we have 3 times cos of 3x. And that is the answer to part A of this example. For part B, we're going to apply the same formula to differentiate g of x, which is equal to 2 sine of 5x plus 7. And as long as the inside part, this 5x plus 7, is linear, we can still apply this rule that's on our formula sheet. So that would give us g dashed of x, the derivative, is going to equal, and the 2 that's multiplying the sine function is still going to be there, so we're going to have 2 times, and then we take the coefficient of x, which is 5, we're going to have 5 times, and it will become cos of 5x plus 7. So therefore the derivative, g dashed of x, can simply be written as 2 times 5 is 10 times cos of 5x plus 7. So that is the answer for part B of this example. For part C, we have the rule h of x equals cos of x divided by 4. And this time we look at our formula sheet and we find the derivative of cos of ax is equal to negative a times sine of ax. So applying that formula, we would find that h dashed of x for this function is going to equal, the a value here is a quarter, so just be careful that you know that x on 4 is the same as 1/4 times x. So we have negative the a value of a quarter times sine of ax, which is simply x on 4 for this question. So that is the answer to part C of this example. For D, we can apply the same formula because the part inside the cosine function is linear. So that means that the derivative, represented by dy dx for this question, is going to equal, and as part of the formula we have a negative symbol, and then the a value of this, which is the coefficient of x, is negative 2, so we're going to have negative 2 times sine of the 5 subtract 2x linear term. So we can simplify the derivative just slightly, so dy dx is going to equal, and negative 2 gives positive 2, and that's multiplying sine of 5 subtract 2x. So that is the answer for part D of this example. And now if you were to put in to your calculator cos of 5 subtract 2x and ask it to calculate the derivative, it would give you dy dx is equal to negative 2 times sine of 2x subtract 5. So that is also correct, as well as the answer that we've got in the box up above. And the reason that that is correct is because sine is what we might call an odd function. And by an odd function, that means that if we have f of negative x, that's the same as negative f of x. So that is a reflection over the y-axis is equivalent to a reflection over the x-axis. Where we had 2 sine of 5 subtract 2x, the calculator has just turned the part inside sine to be 2x subtract 5, so it's factored out a negative there. And it says if it has a negative inside the function, then it could easily represent the same rule with the negative outside the function. So that's all the calculator's done, but the answer we had up here in the box is also perfectly acceptable as well. For part E, we have the function y equals tan of 3x divided by 4. And looking at our formula sheet, we can see that the derivative of tan of ax can be written in 2 ways. The first way is a divided by cos squared of ax, and the second, which is equivalent because sec really just represents 1 divided by cos of x. So the second way we could represent the derivative is as a times sec squared of ax. So we're going to show how to express this derivative in both of those forms in this example. So first of all, if we represent it in that first form, which is a over cos squared of ax, this derivative would be dy dx is equal to the a value, which is the coefficient of x, which is 3 over 4. So we'd have 3 over 4 divided by cos squared of ax, which is cos squared of 3x over 4 for this question. So therefore the derivative dy dx could be written as, and if we have 3 over 4 on the top line, that's the same as writing this as 3 divided by 4 times cos squared of 3x over 4. So that is one way we can express the derivative for part E. And an equivalent way that we could express it would be that dy dx, the derivative, is equal to a sec squared of ax. So the a value is 3 over 4 times sec squared of 3x over 4. So that's another equally correct way that we could express the derivative. And now you might be wondering why we have these two representations that are the same. And the reason why we have it, or I think the reason why we need it, is that this one is the one that you are better off to have if you're then asked to evaluate the derivative at a value, because we know what the exact values of cos are. However, the exact values for sec may not be something you know off by heart. So this first form is useful if you need to evaluate the derivative at a value. The other form may just be a slightly faster way to represent the derivative. And the most important thing to remember is that they are both equally valid ways of expressing the derivative. For part F, we have y equals -1/4 times tan of 2 subtract x. So once again, we're going to calculate the derivative, which is dy dx, and that's going to equal, and now the -1/4 that's multiplying tan is still going to be present in the derivative, so we're going to have -1/4, and it's going to multiply, and looking at our rule, we'd have a over cos squared of ax, where the a value is -1 for this question, so that's the coefficient of x. So this is going to multiply -1 divided by cos squared of ax, but again, as long as it's linear, we can just put in 2 subtract x, so that whole linear term that's inside the tan function goes there. And simplifying that down slightly, this would give dy dx is equal to, and the negative times the negative would give +1 on the top line, divided by, and on the bottom line we'd have 4 times cos squared of 2 subtract x. So that is one way we can express the derivative for part F of this example. And another way that is perfectly valid would be involving the sec function. So our derivative dy dx could be written as, and here the -1/4 times the -1, that's the a value, would become +1/4, and then we'd simply have sec squared of 2 subtract x. So that is an equally valid second way of representing the derivative for part F.